All right, in this podcast, we're going to talk about some neutralization calculations. Specifically, first, we're going to look at how much base do I actually need in order to neutralize my acid. So in the last podcast, we talked about the fact that when you have an acid and a base and you put them in the same system, allow them to react, they are going to form a salt and water. Now, we need to be able to identify exactly what amount of acid or base we need to neutralize said other acid or base. In order to do this, we are going to use our good and trusty old friend, Stoichiometry. All right, so let's look at this one first. So it wants to know how many milliliters of a 0.1 molar solution of NaOH is needed to neutralize 25 milliliters of 0.1 molar HCl. Okay, so first off, let me just point out that we are dealing with a strong base here. So NaOH, definitely a strong base, and then HCl is definitely a strong acid. Okay, so I'm going to teach you two methods by which to do this, okay? So I'm going to teach you the stoichiometry way first. All right, so understand that this is essentially the reaction that we have going on, right? So we're going to make water and our salt, which is NaCl. Okay, so stoichiometry-wise, I need to figure out how much of this do I need to react with that. All right, so I need to figure out the number of moles that I have already present of HCl. So I've got the molarity and I've got the volume of HCl. I can use those to get to my moles. So I'm going to convert this to liters. Okay, and then when we cross multiply and all that fun jazz, we get that we have 0.0025 moles. All right, and that came from my HCl, so that's my H plus amount. Okay, so if I have that many moles of HCl, how many moles of OH or NaOH do I need? Well, hopefully you realize that balance, this equation still has a 1-to-1 ratio. So I need the exact amount of moles of H plus as OH minus. Okay, so this is how many moles of OH minus I need. Okay, so 0.0025 moles of my OH minus, and my volume is what I need to know, and my molarity of my NaOH is 0.1. Okay, so manipulate your equation, and you should get that you need 0.025 liters, which is also known as 25 milliliters. So that's how much NaOH you need of this concentration in order for it to neutralize that much of that concentration HCl. All right, now I'm going to show you a completely different way that will get you the same answer. So let me just back this up for a second. Okay, so we backed it on up there. All right, I left the equation just for conversation purposes. Okay, if your ratio of H and OH is a 1-to-1 ratio, okay, so that doesn't necessarily mean you only have one of each. It means the ratio is 1-to-1. So even if you had like 2 OHs and 2 Hs, that's still 1-to-1, okay? If that is the case, and only if that is the case, you can use this little shortcut called, it's M1V1 equal M2V2. So M stands for molarity, and V stands for volume. Okay? So basically, you're going to put the molarity and volume of, say, the acid, and then molarity and volume of the base, and solve for your unknown. All right, so we know that we have a 0.1 molar HCl solution, and that was 25 mils. And we have a 0.1 molar NaOH solution, and we need to know how many mils of it we need. So multiply and then divide to get your X by itself, and you get 25 milliliters, okay? So that was obviously a much quicker way to do this. Obviously, you probably could have figured it out because these are the same concentrations, but they get more complicated. So I just wanted to show you the shortcut because it is a little bit simpler. Understand that these volumes, you can put them in this equation as milliliters or as liters. They just have to match, okay? So if you're going to do milliliters, both sides need to be milliliters. Okay, in this example, we are asked how many mils of a 0.1 molar NaOH solution is needed to neutralize 25 mils of a 0.032 molar CH3COOH, so acetic acid. All right, so first off, we have a strong base and a weak acid. Okay, so we have one H and one OH, so I can use my M1V1 equals M2V2. All right, so I got 0.032. This is for my acid, and 25 milliliters. And then molarity of my base is 0.1, and I'm looking for my milliliters of my base. So then I solve, and I get 8 milliliters. Okay, so that's how much NaOH I need to neutralize CH3COOH. Now, you might wonder how in the heck I am going to be able to neutralize this weak acid, because we know that weak acids do not 100% dissociate. Okay, I'm just going to abbreviate the acetic part, this whole part, as AC over here because I ran out of room. All right, so initially, you know, we have this in solution, and we have very, very small amounts of the H plus and the AC, okay, or the conjugate base. All right, now, as the base is added, this is a strong base, so as it's added, it's completely dissociating, so you're getting these OH minuses. The OH minuses are reacting with the H pluses and making HOH. So that's the neutralization part, right? They're neutralizing. Now, there's only so many H pluses in solution, right? But as the OH minuses are grabbing the H pluses in solution, it is causing the equilibrium to shift because we're removing the H pluses. So more and more and more H pluses are being made. So more and more of it is making H plus as we continue to remove the H plus by reacting it with the OH and turning it into water. So eventually all of this will be dissociated once we have completed the process and that base has completely pulled it all out of bound form. All right, so let's talk about the pH at the neutralization point. So neutral, most people think, oh, that means 7, right? Well, it all depends on what kind of salt you produce as to what your pH is going to be. And we're going to talk about that in the next podcast. All right, now, the other thing I wanted to go over is how do we determine the pH when we have a mixture of acid and base? So first off, you've got to think stoichiometry here. You've got to determine which of your reactants is limiting and which is excess. Then you're going to calculate your amount of excess and calculate the new concentration of it. And this is a very important section because you got to pay attention to if you've got strong, strong, or weak, strong. situations when you are neutralized. Okay, so here we go. So we have 25 mils of the 0.2 molar HBr, and we're going to react it with the KOH. Okay, so we get an acid and a base. Strong acid, strong base. So when they react, they're going to form KBr and, of course, H2O or HOH, whichever you'd rather, water. Okay, so I need to figure out how much of this I actually have, okay? So in order to do that, I'm going to have to employ my molarity equals moles over liters formula for both my HBr and my KOH. So when I do that to solve for my moles for HBr, I'm going to get 0.005 moles. And then for my KOH, I'm going to get 0.009 moles. Okay, so this is a 1-to-1 ratio here. So because it's a 1-to-1 ratio, we know that HBr is going to be the limiting reactant. So because it's the limiting reactant, it's the one that runs out. And then KOH is our excess reactant. So we're going to lose all of this, right? It's all going to be converted to our salt and our water, which means that we're going to have this many moles of OH excess. Now, that's my moles of excess OH. Now I need to get my new volume. So I've got 30 mils and 25 mils. That's 55 mils, so 0.055 liters. Okay, and then I'm going to divide, and I get 0.0727 is my new concentration of my OH minus. All right, now that I have my OH minus, I can plug it in to this equation. Okay, so I get a POH that is 1.14. And then to get to pH, I do 14 minus POH. So my pH is 12.86. Okay, on the previous problem, you had strong acid, strong base. And again, you had excess of the base. Okay, now in this one, instead of having a strong, we have a weak, strong. Okay, that's the first thing I would like to point out. Okay, all right, so let's go ahead and write the equation. So here's my acetic acid, and there's my base, and that is going to form my salt and my water. Okay, so I need to, again, find my moles of H plus and OH minus by doing some cross multiplying and, cross multiplying and some algebra. Okay, so when I do that, I see that I have 0.0025 moles of my acetic acid, and I have 0.003 moles of my KOH. All right, so the smaller one, so again, 1-to-1 ratio here, right? So my equation is balanced. Everything's 1-to-1. So this is, my acetic is definitely giving me the smaller value. So that's definitely the limiting reactant. And then my KOH is the excess reactant. So I know I'm going to use all of my acetic and most of my KOH. All right, so there is my moles of OH minus. That is excess. And then I have 55 liters when I add the two together. So that's 0.055 liters. All right, that gives me my new concentration of OH minus as 0.0091 molar. All right, and then once again, we're going to do POH is equal to the negative log of the OH minus. So I'm just plugging that number in. All right, so for POH, for this one, I got 2.04. And then 14 minus the POH gives us the pH, which is 11.96. All right, so I just want to point out some trends here for you. Okay, so this problem was a weak acid and a strong base being reacted, and you had excess of the base, right? Now, let's talk about another situation. So, we've got 25 mils of the acetic, and, okay, so this is the same setup, same equation, same reaction as we had before, but now we're given different starting amounts. So that is going to change our outcome potentially. Oh, and I apologize. I just switched to the other form of acetic. These things are equivalent. I just wrote it in a different order. All right, so when I do my molarity equals moles over liters, for this one, okay, I get that I have 0.0025 moles and 0.0015 moles. Okay, so what you should notice is that KOH is your limiting reactant. So that means it's the one that you're going to run out of. So definitely not going to have any of it left. Okay, now what you do have excess of is your acid. So you have not completely neutralized your acid. Now, because this is a weak acid that has a Ka value, I do not have enough knowledge at this point in time to be able to do this one. So weak acid with a strong base, okay, and this is with excess of the acid. In other words, y'all, I know that y'all think that my interludes are really goofy, but my dog is growling at a picture of a dog on the TV. What in the world? Okay, back to this. All right, so I got the weak acid, strong base, and I have excess acid. Because the acid is a weak acid, which means it's governed by an equilibrium situation, I need to pause here, okay? I have got to, I don't have enough knowledge at this point in my life. I'm going to teach you guys about this in a couple podcasts. I don't want to over confuse you. Now, in the scenario that this was not a weak acid, that was actually a strong acid, like say that's like HCl, then in that case, because it was a strong acid, you would still be able to do the thing that we've done the past two problems, which is just find your limiting, subtract out your excess, blah, 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 blah. And that's all because this is not governed by equilibrium. Because the weak acid is the one we have in excess, though, and it's an equilibrium situation, we don't know how to do that yet, but we will learn.